just want to remind you of how we change bases in quantum mechanics, because we're going to be using this result quite a bit as we develop the path integral. Remember when I read a wave function in a position basis, what I'm actually doing is projecting this object that you call the wave function or whatever into a representation that's given by essentially the position. So it's the component of that wave function that can be understood as a position or in the position basis. So what I mean by this is, this is my wave function that's just some, poorly understood abstract object living out there in the ether, and I projected that into the position basis, and that's what psi of x is. Okay, I could also, project the wave function to other bases, of course. So I can look at position space wave functions or, say, momentum space wave functions. And when you take undergraduate quantum mechanics, you deal with the representation in momentum space and how to essentially transform between position and momentum space, right? Let me just look at this transformation a little bit more closely. So imagine I take my wave function. So first off, start with my wave function with no basis defined. And let me insert a resolution of the identity. Let me insert the resolution of the identity in momentum space. And then I can take that wave function, right? So I've just inserted 1 here. I can take that wave function and represent it in position space just by applying the bra to the end of it. Which all it does is leave me with a strange object, x bra p ket, right? But if I compare that thing to, say, the expression for the wave function in momentum space or position space obtained with the Fourier transform or its inverse, then I can actually figure out exactly what this thing is. So it's one way of seeing this is to just write it's either the Fourier transform or its inverse, if you have which one. So if I have something in position space, let me get the normalization right here. I could obtain this from a momentum space wave function just by Fourier transforming. There's my momentum space wave function. That's IPX over h bar. And just to be complete, this momentum space wave function, that normalization is just for convenience. Let's see, dp, so it would be psi of x. And you need the minus sign, p x over h bar dx. Right, so there's various ways to see that. You can look at plane waves and so on. That's really what's going on here. Some plane wave solution. But it's just a mathematical Fourier transform and its inverse. But if I look at this expression here, this is the wave function projected into position space. And so I can compare, the elements of the integrand from this expression to this expression here. So this thing here is just psi projected into the momentum basis. And so from that we have exactly an expression for what x product p is. And that's just this normalization constant and the exponential here. So it's xp. So you can think of this as being the wave function. So I guess the momentum wave function. In position space. Right, so it's a little weird, but that's all this thing is. We're going to use this when we develop the path integral later in this class. So that's just a review of something we do in undergrad. Let me go check on Mac here. I'll be right back. You guys like that? That's fine. It's cool. Nothing weird about it. So it's just a change of basis, basically. We can also employ changes of bases in second quantization. In fact, we'll do it all the time. So let's go back to second quantization. Last class, I introduced the raising and lowering, or the creation and annihilation operators for second quantization. So I call them A dagger, I, maybe AI. And remember, they take a occupation number of that single particle state, which is labeled by I, and they raise it or lower it by 1, basically, with some normalization. So these things actually, they actually operate in the single particle, or on a single particle state. So and we started by writing these single particle states in the position basis, okay? And I probably labeled them something like psi I, that's the single particle state, R. I'll leave the index off of the R. So if it's actually just a single particle, all this is, I guess I would write it like this, something like that. Okay, so just a way of labeling, R is just a way of labeling particles in some sense for us. But I could also imagine writing the second quantized annihilation, creation and annihilation operators projected into a different basis. So let me just take the annihilation operator. I could say, well, maybe what I'm doing here is inserting a resolution of the identity for the single particle states, just like I change basis for, I don't know, this wave function object here. Now I'm doing it for an operator. And what this thing is the thing that I've been using. I'll call it, I'll just call it AI, which explicitly labels the annihilation operator to operate on the single particle state that's labeled by I. Okay. But then I could change bases by defining the operator in position space, which you could think of as something like that, which would just be R phi I AI. And then we know what this thing is. This is just phi in the position basis. So sum over I, phi I R, AI. So the raising or lowering operator, there's another expression for the raising operator that's basically this, just do the same thing. You'll complex conjugate this and put a dagger here. But this thing's just called the field operator. What the field operator does is create a particle or annihilate a particle at position R. I'll write that. And so they're called field operators because what you're doing is using them to define a field theory. And the particle is just an excitation of the field. Okay, so. So writing these field operators is, in some sense, the first step to defining a field theory. So what we should imagine is some sort of vacuum state, and the field theory can be defined it's fine to define the field theory in position space, even though we threw away, R in terms of single particle labels. We can still define the field raising or the field lowering operators in terms of those single particle wave functions. And what we're going to do is we're going to take these field operators and use them in a d+1 dimensional path integral expression in order to write the full field theory for the many-body system. So that's one thing I wanted to make a note of in terms of second quantization. We can also change the basis of the raising and lowering operators. And the last thing I want to mention about second quantization, which I didn't get to last time, is second quantization of operators. Okay, so we've talked about Fock space, right? And we know how to operate in Fock space with raising and lowering operators. But what if we have operators like occur in a Hamiltonian? Might have momentum, or single particle operators, or the Coulomb interactions, or something like that.
Aren't the size that you just defined operators?
These are operators, yeah. Mm-hmm. Okay. So this is an operator, and this is an operator, yeah.
Is that like standard to use size?
Yeah, that's why I would like to use maybe A, you know what I mean? But in textbooks, you'll see psi as operators.
So when you introduce the resolution of the identity, you just use single particle state as a basis, but the Fock space has any particle number. So
right.
Why can you do that? Like, I mean, it doesn't sum up to 1 unless you pick the sector in the Fock space.
Unless you pick the what?
A sector in the Fock space, right?
Like a single particle number sector? Yeah, so it's an issue with normalization, I think, in that sense. But you can just think of this as, I mean, what I'm doing here is just motivating what I think is actually, this is the definition here. So I think if you read a textbook, you'll just see field operators are defined with this basis transformation. But yeah, just an analogy to what so there are some subtleties with basically the normalization of Fock space, I think. But just an analogy to what we did here. That's all I mean by that. So if you read your book, you'll probably see that definition. Right, so these are operators. These are second quantized operators. But if general operators like occur in a Hamiltonian also have representations, and I'm going back to A's. I just want you to be aware that these psi's exist. But let me go back to the raising and lowering operators in the occupation number basis. And the most important operator besides maybe A and A dagger is the occupation number operator. And just an analogy to a simple harmonic oscillator. You can write the number operator as an operator n that looks at a single particle state and returns the number of particles in that state. Okay, so go back and look at your simple harmonic oscillator, your simple harmonic oscillator theory, and you'll see the analogy immediately. So I use n to operate on that state I, and I have an occupation number representation. Then all I return is that number. So some textbooks use a big N to distinguish the operator from the eigenvalue. But this should just return that number. And check that it works for bosons and fermions. It should be straightforward. And the reason the number operator is important is it occurs in second quantized, say, Hamiltonians and so on, quite regularly. So unlike A or A dagger, which aren't Hermitian, it'll give you a Hermitian operator. In Hamiltonians, you'll have operators that can look like kinetic energy or hopping operators in second quantization. You could have on-site terms like the fields, like the transverse field or the longitudinal field, or things like Coulomb exchanges or Coulomb interactions between different particles. So we can basically transform between first quantized operators and second quantized operators. And by first quantized, I should be writing things that are familiar to you. So I could write a many-particle Hamiltonian that, for example, has a kinetic energy term written in terms of momenta of the particles. I could write it like that. J's labeling my particle number. I could have other single particle operators. So I have a sum over J still. I could have some just general operator. Call it U. Could be a magnetic field or something like that. I can also have two-body operators. Ones that operate between two particles, right? Just like the Coulomb interaction, or some sort of magnetic exchange in like an Ising model. That would be like your J term in the Ising model. Your Ising exchange would be a two-body operator. So quite generally, these are just, you have two sums, I and J, which run over the number of particles. The term doesn't operate on itself, so that's U. These are usually, you can usually write these Ri minus Rj, but generally they're just functions of the two. You can have higher order operators, three-body operators, four-body operators, and so on. So you can take that very general first quantized, right? This is Hamiltonian, or each one of the operators, and transform it into the language of second quantized many-body Hamiltonians. And I'll just give you the prescription for sort of how this is done. So I'm not going to derive. So let me just give you a flavor for how these things are basically looked at. So let me look at maybe the single body operator, the one body operator. I'm going to call it U. That's a 1. It's this thing summed over all particle numbers, all particle indices. R just labels the particle number. And you can have different types of one-body operator. They could be diagonal or off-diagonal. Like in the transverse field Ising model, the transverse field is off-diagonal. Off-diagonal. And the form of the second quantized operator depends on how that looks. Depends on whether you're diagonal or off-diagonal. Second quantized operators. This can be derived rigorously, but we spent enough time on this. So just as motivation, second quantized operators are constructed by considering matrix elements. And let me look at the diagonal case. So I would essentially sum over all single particle states. And insert the one-body operator to calculate all the matrix elements. So I's are my single particle states. J is from the Hamiltonian. It labels the particle number. So this type of matrix element is what gives you the second quantized form. Pardon?
You're taking the trace there.
Yeah, trace over all single particle states, basically, yeah. But all single particle states, right? So you could also write this as a matrix element of the ensemble of states or something like that. But here it's just a simple trace. So if this is a diagonal operator, basically what happens is every time you have a particle that's labeled by R of I, that's in a single particle state, phi of I, you'll operate on that state. And if it's diagonal, you just get some matrix element out of that. That depends on the form of U, right? And then the inner product of phi's. So if you sum over single particle states, I don't know what that matrix element is, but then it's a sum of all times that single particle label operates on that single particle state. That's only for diagonal. And then this thing here is just the number operator that I introduced. Or it's just the eigenvalue of the number operator, I should say. So you can transform this scalar quantity, right? That's just the trace, if you will, or the sum over all these matrix elements, into an operator by just recognizing that every time, you'll get one contribution to this sum every time this particle label, this particle R of I, operates on that single particle state. And that's kind of the idea. You take these matrix elements and then form the second quantized operator from that. And so then what happens in the second quantized operator is you have all of these matrix elements, and in this case, the number operator. So it's a sum over single particle states. Multiplied by some weight, multiplied by the number of particles in each state. And if you're not diagonal, you'll get a similar form for the one-body case. So if you're off diagonal, Then your second quantized single or one-body operator is just sum over, let me use alpha and beta for the single particle states. So we can keep track of these indices. This thing isn't the number operator anymore because the dagger will operate on alpha and the annihilation operator will operate on beta. Okay, so I'm not proving any of this. I'm just writing down the forms. That's a diagonal one-body operator. That's an off-diagonal one-body operator. So it kind of makes sense. And the whole problem with transforming between first and second quantization is calculating those matrix elements. Two-body operators, which are important for interacting quantum systems. So the U of the Hubbard model, or something like that, or the Coulomb interaction of the Hubbard model. What do I call them? V? Okay, I'll call them V. So the second quantized. Let me start with the diagonal operator. Let's write this a bit more compact. So this will be my small v. A alpha, beta, beta, alpha. And again, the problem is calculating the matrix element. Okay. And if you're off diagonal, I need 4 indices. It's analogous to the one particle case. Alpha, beta, gamma. Yeah, that's right, delta. So I used to make students derive these second quantized operators in this class, but I don't know. I don't think you actually learn a lot from that. Because quite often what we're doing is we're starting with second quantized Hamiltonians, right? But at least if you look at the form of these transformations, especially the particle, the number of raising and lowering operators, right? And the number of indices, you can tell the form of the first quantized operator and vice versa. So I think that's really the point that I'm trying to get across here. So for example, a first quantized Hamiltonian looks like that thing up there. A second quantized Hamiltonian will just look like, let me write something I can think of off the top of my head. So here's the second quantized Hamiltonian for a lattice Bose-Hubbard model. Now the raising and lowering operators for bosons are often written as B's. I could have an on-site Ni minus 1 or 1/2. I don't care. I could have an on-site repulsion term, attraction or repulsion, depending on the sign of U. I could have a chemical potential, right? So that's a typical second quantized Hamiltonian. It's called the Bose-Hubbard model. So you start to see things like this hopping term. So if I have a lattice, and this specifies nearest neighbors, just like it did for the transverse field Ising model, what this term in the Hamiltonian does is take a particle that's on site J and annihilates it with B, but it creates a particle on site I. So they call it a hopping term because it effectively moves this particle to its neighboring site. Okay? And that's like the kinetic energy operator. That's what this term here would turn into, which is like an off-diagonal single particle operator in the Hamiltonian. Right? So you have two different labels, I and J, basically. And you have longer range hoppings and so on. But so these T terms are often called kinetic energy terms. And these are potential terms. This is a chemical potential. And this is something you can imagine coming from whether or not you want two particles or more on a site. Okay? So all these things can be transformed back and forth between first quantized and second quantized. But we're going to be dealing now only with these second quantized types of Hamiltonians, or mostly with these second quantized Hamiltonians. Okay, so what we're doing now is we're taking the second quantized operators and we're performing this path integral, or this Feynman decomposition into a d plus one dimensional object that's purely classical, in the same way as we did for the transverse field Ising model. So just to keep track of where we've come and sort of like the path that we're taking, we've gone from single particle quantum mechanics where I have a wave function in position and time. So your usual idea of a wave function. And we've discussed first quantization, which takes that same wave function and the same sort of philosophy of a wave function and extends it to 3n dimensional space. So 3-dimensional space. So all we do is we have labels for all of our different particles then. And you can have a time to keep things general there. So it's just 3n dimensional space. And we haven't actually used first quantization, but I think it's logically the next step in the progression. Then we've argued that we want to perform we want to perform many particle quantum mechanics in the second quantization. And this means that we promoted the wave function, which is this sort of vector object, if you will, to an operator, A dagger A, or in terms of fields. I think this is why people use psi. It's because we've started using the description of raising and lowering operators of particles in the field theory, right? So we've gone from 3-dimensional space to 3n-dimensional space to a 3-dimensional space that has creation and annihilation operators. Okay. It could be like a lattice in this sense here, right? In the transverse field Ising model, the creation and annihilation operators, what would they be? So think of what the vacuum state is, or think of what basis we're in. If say we're spin 1/2, angular momentum operators, then the basis we're operating in is whether or not we have SZ spins up or down, right? So say if a vacuum state's a ferromagnet, everything pointing up, yeah, which is just S minus, right? So the analogy of the field operators for the thing we did at the start of class for the transfer field Ising model would just be the S plus, S minus operators, or sigma plus, sigma minus operators. Right, so that was kind of a, kind of a toy field theory, if you will. And then the final step, which we have yet to perform now in the general second quantized case, is to promote the field operators, the raising and lowering operators, to the path integral representation. So now these size, they won't be operators anymore. They'll be integration variables. So the functions of 3D space and time. Okay, so you have an extra time, which is going to be, we'll see, related to this t. It can be different through Wick rotation. And so now we're actually integrating over variables. We've gotten rid of the operators, just like we did in the transfer field Ising model. And we're going to integrate over variables in a higher dimensional space. So we get rid of the operators at the cost of this functional integral. So that's kind of the philosophy. So the question is whether or not you gain anything by throwing away the operator representation of quantum mechanics. I mean, that's for you to decide. So let's go on and start doing step 4, okay? The sort of last general step to construct the path integral. So before we get into coherent states for bosons and fermions and all this stuff, let's just rederive the d plus 1 dimensional expression like we did for the transfer field Ising model, but let's do it for the single particle case. Okay, so this is something you could have done in undergrad, but in my experience, most people don't do this. So we're just going to start from scratch. Start with the Schrodinger equation. Oh, and let's just work in one-dimensional space. So I got the full time dependence. On the left-hand side, I have the time derivative. On the right-hand side, I just have the Hamiltonian. And if the potential here is not time dependent, right, then we can write the time independent Schrodinger equation, and we can write the time evolution operator. So we're going to use that time evolution operator that comes from that assumption that v of x doesn't depend on time. So let's write the time evolution as taking the wave function. Okay, just gonna write the time dependence here. Okay, so I've yet to project this into the position basis. And let me call this thing u, not to be confused with all the u's that I wrote over here. I don't know. I wrote these at a different time in my life. And that time evolution operator, as you know, let me write it with all the h bars. That's the Hamiltonian, and it's not the Hamiltonian as a function of this. It's t prime minus t in the Hamiltonian. So I'm taking a wave function at time t and time evolving it to time t prime. Something like that. And let me assume this might become important later on, that t prime is greater than t. Okay, so let me take that first expression. I'll work with u. Just remember that u is the time evolution operator. And let me write this in position space. So then I'd say x let's call it x prime. Okay, so I've just written a matrix element. But now let me insert a resolution to the identity. Which is somehow the only trick in quantum mechanics. Which will give us an integral over x. And just get all these labels right. X prime. Here's my x from the resolution of the identity. So here's my wave function at time t projected into the x basis. That's what I wanted. So this object, which is a wave function at a later time and a later position, I'm just going to write as, so the integral over this matrix element. So I got to label x's and t's. X, t, that's a semicolon. And then this thing is just psi xt. Okay, so like we're used to, the wave function at a given time and space, can be used to predict the wave function at a later time and a later position in that space through this, what they call like a propagator or something. This combination of time evolution operator, really the matrix elements of the time evolution operator. So all the information you want to know about the time evolution of the particle is contained within that integral. And so what we do in constructing the field theory is consider directly that u of x prime t prime xt. We look directly at the time evolution propagator. So this is the object that we're going to insert a bunch of resolutions of the identity into, but after defining a small parameter, okay, and solve for the matrix elements, okay, in order to make that thing completely classical if we can. So over h bar. That time interval that we wish to perform the time evolution over, right? T minus t prime. This is the thing that we're going to decompose into small intervals. Just like we had, what did we have? We had the partition function for the transverse field Ising model. So we had something like beta, right? So we divided beta by some integer number. So let's divide that time interval into a number of steps by dividing by some integer. Oh, damn. I used big N throughout my entire notes here. I'm not going to change it now. So I used M before, I just realized. This is the integer that, was M. So it's not the number of particles. So in 2 weeks, when you look back at this, don't be like, what's the number of particles doing in there? It's a single particle path integral we're deriving. So it's just some large integer. And delta t is like I think it was called like epsilon before, right? So m times epsilon was your beta before. Yeah. So just like epsilon. So we can also, am I going to need this? I can also label, I think it was L, was what I used before. So we can label the time steps. With K instead of L. So the time at some, step in this interval, which we're going to derive between t and t prime, is just K times that small interval delta t. I think that's it. So let's look at the full time evolution. So then let's just look at the time evolution operator. So I'm going to do t prime t n minus 1. So all the way down to t2, t1, u, t1, and t. So I'm gone from t to t prime. Okay. And I've stepped this up by k delta t. And now what I want to do is insert resolutions of the identity in position space between every single one of those time evolution operators. Okay, so I have n minus 1 of them. So the first one I'll insert here. So I got to label my x's, which is annoying. But what else can you do? That's one resolution of the identity. I'm going to do another one here, say. So if that's n minus 1 on the right, so this will be t, this will be 1. So dx1, x1, x1. Okay, so the path integral is coming along. That's the position in this like series of operators. So I've broken the time evolution operator into these discrete steps. And so I've inserted the resolution identity n minus 1 times in between each one of these products, if you want to call them that. It's the same thing we did with the transverse field Ising model when we had, I had defined the operators there in terms of the Ising operators, J and H or whatever the hell I called them. And then I used the Trotter decomposition there, so I haven't assumed that yet. I've just broken up the time evolution here. But there I used the Trotter decomposition to write a whole bunch of products of exponentials or something, and I inserted resolutions of the identity. Same thing here. So each one of these is unique, right? So each one of these integrals has to have a different integration variable. So that I could have wrote it as a subscript or something like that. So I'm just keeping track of all those different integration variables for all those different resolutions of the identity. Okay, so let's look at this matrix element in full. Lost my chalk. Nope. So I've inserted all the resolutions of the identity. So the matrix element, which has the position space. I'll pull all these integrals out. Okay, so let's see. So I have this integral here, so I can just pull out and my last one's 1. Yeah, that's just all my integrals that come from all these insertions of the resolution of the identity. And then I'm integrating over I should use subscripts. I'm going to partially fix that by using it on my t's. So it'll be x1, t1, because the last one is just x and t. Fit. All right. Good? Okay, so each matrix element which is just like last time. You know, we write this thing, but then it's evaluation of the matrix element, which was kind of had all the tricks in it, right? Remember last time we had all those cinches and coaches and everything? So quite generally, we're going to write this matrix element. Right, as the time evolution, so it's I over h bar, minus, I guess, and t, a small interval, so it's just delta t, and this is k. So we have somehow basically the same matrix element we had last time. But I'm not really assuming anything about h here. Last time we used the Trotter decomposition because we had two terms, like a diagonal term and an off-diagonal term. This time I'm just going to assume delta t is small. I mean, this time I don't really have to assume anything. The exponential of an operator, the Hamiltonian operator, right, is defined by its Taylor expansion. So let's just do the Taylor expansion. But that Taylor expansion in the limit where delta t goes to 0 is just going to be 1 minus all this junk up here. I have a minus sign, but yeah, you know what I mean? So I can just approximate it with its Taylor expansion, and we're completely safe. Which puts me in position to just calculate that matrix element of H. So this is true for delta t, okay, less than less, very small. Okay, this is not maybe strictly a necessary step, but it'll make a lot of sense when we evaluate the matrix elements. Okay, so let's perform this. Let's evaluate this matrix element. So we've expanded the exponential. And let's do something weird. Let's do it in momentum eigenstates. Oops. Okay, so we're going to expand in momentum eigenstates. So resolution of the identity. Right here. Hamiltonian. Why do I keep doing that, right? In this case, having a momentum state around helps us because we can assume the single particle Hamiltonian is written in terms of P and X. Okay. So P squared over 2m or something, maybe for kinetic energy, plus potentials that depend on the spatial position, right? And then H is Hermitian. It's a Hermitian operator. So we can operate, you know, H forward, all the X parts of H forward and all the P parts of H backwards. If you want to think of it like that. So as an example. Oops. So the Hamiltonian might look something like this. X is an operator, whatever it is. Right, so this operator pulls out P from operating on the bra, and this thing just pulls out whatever functional form of V is operating forward on the ket. All right, so you get like the Hamiltonian evaluated at those values of P and X times that matrix element. Maybe I'm writing too many steps here. I don't know. You tell me if you're bored. But now what I do is I can write the matrix element, okay, just with the Hamiltonian. So this is just the Hamiltonian evaluated. It's just a scalar quantity now, right? So this thing here, then I'm going to say pk, right, so pk xk, and the Hamiltonian, which is no longer an operator, so this is an operator, this is not, it's just the matrix element, or the Hamiltonian valued at x and p from the matrix element. I don't know if that's useful or not, but let's write out the Hamiltonian.
Don't you have to, since what you're going to evaluate over there has an I, you have to take into account this unitary? You get the Lagrangian.
Yeah, I'll show you. Yeah, you do have to take that into account. Yeah, we're writing this as an action, so you'll see the Lagrangian come out. Okay, so let me write out the Hamiltonian. So this is assuming that expansion, right? Okay, I'm officially writing too many steps. Delta T, H. That's my Hamiltonian. Oh. Yeah. Did I do something wrong here by writing too many steps? Yeah.
When you act backwards with P, you should pick up a minus sign. When you act backwards with IH.
Yeah. So, but wait, what am I writing here? So that's my matrix element. No, that's just my matrix element of H.
That's right.
Yeah.
But down here you're doing the
But this shouldn't have been H in here, right? It should be this thing in here. Oh yeah, sorry, that's just the matrix element. Oh yeah, you're right. This thing is the matrix element of this is U of xt. Sorry, just let me clean this up first. So this is U x. Yeah, x prime t prime, right? And sorry, H. Yeah, so this is okay. I was just writing the matrix element of H here. But H is p squared in it. Okay, so what are you saying?
I'm saying that you're not actually, when you take the matrix element of U, you're taking the matrix element of IH. So when you act with IH to the left, you pick up a minus sign because of the I.
That's right, yeah.
So you should get, so what you wrote above is correct because you're doing the matrix element of H.
Of just of H, right.
But if you're doing the matrix element of IH up there, you would end up with minus p squared plus v of x.
Right. So why are you saying plus p of x?
Pardon?
Why are you saying plus p of x? Oh, minus p squared plus v of x.
Minus p squared Plus v of x. Sorry,
plus v of x. Yeah. That's fine, right?
Well, you just, in this line down here, that should be negative I over h bar delta t, and then actually it should be plus I over h bar delta t Lagrangian.
Right, because what we're doing, okay, so we've expanded this out here, right? So we have to operate, yeah. Is that right? I'm not convinced.
Yeah, you have to operate with IH though.
IH is just a scalar, right?
I when you take it to the left.
So I pull a scalar out front.
No, not because an inner product is not. It's what's the word? It's like not linear. It's the other one, complex linear. It's like when you have a.
I mean, if I have an inner product, I don't know.
So you agree that the operator
So
is not Hermitian, right?
If I have phi c psi or something like that.
And that's a scalar.
C's a C number, yeah.
Right. So now
is this equal to C psi phi?
No.
Or is it C star psi phi?
So the way you've written it is ambiguous. So is the C acting? So if you wrote it.
How do you act with? Okay, so it's just a number, right? Just a scalar.
Right, so imagine if you wrote it as the inner product of phi with C psi, then it would be the first line, and if it was the inner product of C phi with psi, then it would be the second line.
I agree if you have an operator. Yeah, we have to be careful here. This is important. So if you have an operator that operates, okay, wait. Okay, so you're saying that whether or not I have this, or whether or not I have this.
Yeah, those are different things.
Only if C is an operator.
But C is a scalar.
If C is a complex number.
Yeah, it's a scalar. It's a complex number.
Just imagine doing an inner product of two vectors on C2.
On C2?
Yeah, like the complex plane.
Okay.
So imagine I have a vector that's say, Z1, Z2, and I take it, there's a vector that's two complex numbers and it's Z1, and there's another vector Z2. So if I do the inner product of Z1 with CZ2, right, that's supposed to be Z1 dagger, right, complex conjugate transpose on, well, here, I'll just write it down.
I know what you're saying, but I'm not convinced that that's,
No.
it's just a scalar, right? I mean, if you have a scalar, am I wrong? Everyone else,
if you take
what do you
I
guys think?
No, it's P and X are Hermitian, so the fact that there's a complex scalar multiplying them doesn't change anything.
That's what I think. Yeah.
No, the scalar rules. The spectrum of those operators are totally real, so they're Hermitian.
I disagree with that statement. If I take the matrix I times the identity, that's not equal to its complex, like its conjugate transpose.
Okay, let's keep going, and we'll sort out that minus sign later. So the debate is about this. Okay, so in this matrix element, I'm just writing the matrix element of the Hamiltonian. Here I'm writing that full matrix element. This is the thing under dispute, right?
Mm-hmm.
Okay. So let's keep that sign in mind. Because I just want to basically write, well, the Lagrangian, but I might not get there. So let's keep that in mind. So what we're doing now, okay, so actually, does anyone recognize this before I move on? It's the thing I did right at the start of class, right? So this is the, what did I call it? The position space wave function projected into momentum space or something like that. So let me pull out, remember it's 1 over 2 root 2 pi h bar. So let me pull out a bunch of these. Let me pull out this term. So it's, okay, now write this in terms of, yeah, so there's my delta t, there's my Hamiltonian. Okay? So what I have here is I basically have two of these matrix elements. So one gives me an x at k plus 1, one gives me an x at k. Okay? So I have like a delta x in some sense. So I have a difference in time, space, and I also have a difference in time. So this is the same structure that came out of, remember the transition field Ising model decomposition into d plus 1. So one more step. I don't know if you guys can see here, but yeah, I'll move over here. Actually, I think I can just insert. I think this is good enough. So let's move on and let's insert this term for every. Right. So this is this is just this matrix element. I've inserted resolution's identity into that. I want to insert this for every term in U of x. In U of xt. Okay, now give me I forgot to label this. Just keep track. What I was doing here was just k, k plus 1, these are the k labels, k plus 1, k plus 1, k, k. So I have a whole bunch of those I have to insert, right? So when I do that, I'll get all of these integrals. So a whole bunch of momentum integrals. So every single resolution of the identity that I've inserted gives me a different p integral, and all of my dx integrals, which go from n minus 1 to 1. And inside the integrand, the matrix element which I'll write like this now. So P of k, x of k. Okay. Too many brackets, but right, I think that's right. So that should be right, this propagator. So p minus 1 to p naught for all the resolutions of the identity, and all the integrals over dx, right, and the exponential. Okay, so the final thing to do is to take essentially this delta t to be very small and write the sum as an integral. Okay, so I've imagined inserting a discrete number of n resolutions of the identity here. Okay, so let's take n to infinity so that delta t goes to 0. So dk, which in discrete form is just this. By chain rule is like, or sorry, dx. So it's like dx over dt. So that's the same as saying x prime. But by chain rule, you need another dt there. And my sum over dt's, or delta t's, if you will. So let me do this so I have two delta t's. I got one from here, one from there. So then my sum over k delta t just becomes that integral. And I want that integral to go from t to t prime. dt. Good. Okay, so finally we can write an integral expression. So let me collapse everything back down. And all of these, just like I did for the transverse field Ising model, I have all these integrals out front, and I have all these, and then I have the integrand, and all these integrals out front are the functional integral. So I think I just call them like square bracket product of a whole bunch of probably those sums for the transverse field Ising model. Here I'm going to use functional integral notation. I need another t, because I have t and t prime already for the integrand, so I'm going to use t double prime. So that's an integral over, a functional integral over p, and a functional integral over x. T double prime.
I don't know if it's worth commenting about the sign right now, like the way that it's written upstairs in the discrete form. It's just the geometry transform of the Hamiltonian, which is the Lagrangian. So that's where your sign is.
That's where my, so I'm going to write it in terms of Lagrangian right now. Well, yeah, I'm there. Yeah, thanks. So the functional integral, let's see, and the integrand, so because here I have to use t and t prime. Minus t double prime. Oh man, I think I got it all. And then dt double prime. Yeah, that's what you're saying. This is, oh, did I forget an x dot somewhere? Right here. This is your Lagrangian, right?
Sorry, how did you get I over h bar delta t inside the exponential?
Yeah. It's like you expand it and then collapse it. It's like you re-exponentiate it. In three-dimensional space, basically that's like your Lagrangian, right? And so what you've done is you've written a functional integral, and recall the action. The action is just, the time integral of the Lagrangian, something like that, right? And so what you're doing is writing this in terms of, a functional integration essentially over, e to the action or something like that. And the difference between classical and quantum mechanics is classically you find the extrema of all of these different paths or all these different actions, right? The extremal path. But in quantum mechanics, what you have to do is you have to do this integration over all of them. And so even though you figure out the matrix element of your Hamiltonian in some sense, right? What you've lost by throwing away all the operators is basically this functional integral over here. Okay? And so that's the price you pay, but that's the path integral. That's how we write it.
What's that d3? Yes, I missed it.
What are these functional integrals?
Yeah.
They're these things here. They're all these things. They're all these integrals that come from all the resolutions of the identity that you've inserted willy-nilly in order to basically evaluate the matrix element. So you have to keep that in mind what basically the definition of these things are when you're dealing with a functional integral.
So this is a Feynman path integral in the phase space, right? Rather than in the configuration space, because you still have x and p, which are canonical variables.
Right. So I'm going to talk more about that next time. I just ran out of time.
Okay.
So this is important somehow here. Okay. This is what gives rise to your Berry phase, basically. So there's still something you have to be careful with. I mean, it looks classical. I mean, you might start worrying about this I. Actually, if you do a Wick rotation, which I'll do next time, and you write the partition function, then you'll see that everything becomes classical if you can get rid of this term by some essentially Gaussian integration somehow. And if you can't get rid of this term, if there's still basically, an imaginary product of x dot and p in whatever form those two variables take in your problem, if you can't get rid of that, that's your Berry phase. And you might argue that Berry phase is what's actually quantum mechanical about the problem, about your path integral in the end. Okay. So I'll keep going on Thursday. We'll look at this a little bit more. And if you got assignment issues, let's discuss them now. Or this minus sign if you want. Let's discuss this now too. So I'll see you guys Thursday.